In this lecture on optical lithography, we are going to look at mask technology. So far, we looked at the imaging process, the resist process, and how to create the patterns on the resist, right, using the image formation technique that we explored in the few lectures earlier. So now we would like to see how these masks are made. Masks is repeatedly used in this optical lithography, and we need to understand what kind of technology is used to make this mask and what are the specifications of this mask layer. So this is just to recap what we are discussing here. In the projection lithography system, mask is the primary element that has all the circuit or desired patterns that we would like to project onto the wafer. So it is basically a template, right? So we can do n number of times without causing any damage in this particular scheme, but in contact lithography, you are going to make this mask come into contact with the wafer, right? So irrespective of whether you are using projection lithography or contact lithography, the mask patterns are nothing but templates with desired circuit patterns. So it allows us to replicate the structure on the wafer, and you want to have high throughput. That's a primary idea of using a mask instead of writing, right, each and every structures that you want to have on the mask. And there are two things, right? So it should have a transparent region and also opaque regions, right? So the mask should have transparent and opaque regions that will define the structure, right? And the mask should be defect free, right? We only want the structures that we want, and we don't want any additional features on the mask. And this is what we call defects, right? And the defect could be either from particle or some cracks on the mask and some transparency issue, the place where you want it to be opaque. If it is transparent, then that is also a defect on the mask. And then roughness, right? So ideally you want a line to be very smooth, right, an resist line, let's say. But then if your mask has roughness, then this roughness will be transported to your wafer as well. So all these are considered to be defects, right? So we should have a defect free mask layer. And the other thing is, we don't want any artifact or undesirable distortion, right, transferred from the mask onto the wafer. So there are multiple artifacts, right? It can be structures that are undesirable, which are sitting there, which is not developed properly, and there are no precise edges defined. So these are all the things that will create undesirable distortion on the image that you want. So in optical lithography, this photomask is used to transfer the pattern, right? But then we want to understand how we make this mask, right? So how these masks are made and what are all these properties of mask. So that is going to be the topic for this lecture. So this is a GDS file, right, or you can say a design file that has a lot of features, right? So we have a circuit here with different colors showing different layers in lithography, and this is the design that any circuit designer will come up with, right, and he has these circuits there, and we want to transfer this circuits onto the wafer. But there are some interesting features on this mask, right? We saw earlier that we want to align the masks, right, of different layers, and we use some alignment structures, right? So this is a zoomed in picture where it shows this crosses and boxes, right? We saw earlier how do we align it, right? So we saw alignment of this cross with this type of structure between two different layers. That should give us an alignment between two different layers. So this is also put on this mask. And then at the edges of the mask, you will see features like this, right? So there are some line space features which we can use as a metrology structure. So we cannot measure each and every circuit that we make, right? Each and every device we make, it is impossible to measure those. So what we do is we put some measurement structures at this edges, right, what we call scribe line. So these edges could be used for measurement of the structure. So since we are illuminating the whole mask with the same amount of energy, you expect the structure on the scribe line or the edges also yield the same dimension as you have on the center of the mask as well. All right. So let's look at the process of making this mask, right. The first thing is the design. As a designer, you come up with the circuit pattern or any kind of desired pattern, but primarily you use some EDA tools, right. So you use a EDA tool to come up with this design, and you will use patterns, right, defined as a hierarchical structure, right. It depends on the strategy people use. What I mean by hierarchical structure here is you define a simple square, right, and if I want to draw any pattern, for instance, if I want to draw a circular pattern like this, so what I would use is I will use this square to arrange it in a certain fashion. So now I am using the primitive here to define my ring here, or let us say I am drawing a line. So I can use this primitive to draw these kind of features. So this will allow you to reduce your overhead on your design, right, and it depends on the design strategies. This is one way of doing it. And when you design it, you get a certain format. GDS or OSS format is the format of the file that you get, right. So now this is all designed, right. You can look it up in your screen in your EDA tool. It will be a two-dimensional structure, right. So it will have some lines, right, or holes, right. So this is what you will see. So now you want to translate this onto the wafer, but before that you want to do some Boolean operations, right, in order to make or create desired structures. Right? There are multiple ways to do that. So this Boolean operation is done either by the designer or during data preparation. So normally these Boolean operations are opaque to the designer. So this designer work ends here in providing the GDS to the lithography team or the mask prep team, and this mask preparation team will look at the data, and then they will do Boolean in order to get desired structure. So what do we mean by Boolean? So for instance, I want to draw a line like this, right. So as a designer you will draw a line, but then if the mask is dark field or light field, we'll look at it in briefly what this bright field and dark field means. So I want to have an opening here, right, and then I want a opaque regions all over, right. So you only design this line, right. So how do we go from this layer to this layer, right. So how do we do that? So this is where the Boolean comes in. So Boolean here could be an AND operation. So if you do a AND between the structure and then a large patch, so what you will get is something like this, right. So these Boolean operations are done by the mask preparation team, and then the mask preparation team also converts the data format, right. So the GDS is the design format that you give. This is the graphic design system format, and they will convert that into a different pattern generator or the file format that is required to write the mask, right. So once this data preparation is done and the file is sent to the mask shop, right, and this mask shop is the one that's going to make the mask for you, and this is the stage what we call tape out, right. So once you design and then you send all your designs within appropriate mask file format to the mask shop, we call that as a tape out phase. So once the tape out is done, then the mask file is sent to the mask shop, right, and there it goes through various fabrication steps, and this is a summary of it. So the mask preparation is done, and then we take a blank mask, right. So we want to make transparent and opaque regions, right. So we take a substrate, and the substrate is covered with, let's say in this case, a chromium layer, right, which is opaque, right. It's a blanket layer. So this is what we call blank mask. And then we do exposure. This is similar to lithography, right, and this mask layer will have a resist, right. So this could be let's say a photo definable material. This should be a photoresist, and then we expose this. In a minute we will see how we expose this without using a lithography step. In particular projection lithography step, we expose it, right, and then we do the resist development, resist descum. So descum is nothing but clearing out any resist that is undeveloped, right, sitting at the bottom, right. So we remove that using descum, and now is chrome etching, right. So we etch the chrome now. So we remove the chrome underneath, right, and then that should give you a nice pattern, or opaque regions are defined, and then you define a transparent region here, considering this is glass, right. And then we strip the photoresist, we clean the mask, we characterize it. This is very, very important step. We characterize the mask, we measure all the critical dimensions that is given as a specification. We characterize this mask, and then if there are some issues with the mask, we repair it, right. It is possible to repair defects, and that is also done without redoing all the steps. There is a repair step, and then after repair you clean it, again you characterize it, right. You want to make sure your repair has worked or not. Once the repair is done, you add a pellicle, that is a protection layer that you put, and then you deliver the mask. Okay. In some cases at this step you will find out that your repair has not worked, or even at this step, in the previous characterization step, you have found out that your mask is completely out of specification. So what you do is you start from this process again. So there is no way to rework this mask. So this is one of the reasons why, if the specifications are very tight, you are asking for critical dimension variation within less than 1%, or critical dimension very close to the resolution limit of the mask process, your mask will be very expensive. That expense comes from this process that we have to repeat and get the required critical dimension or specification. So the mask plates, this is a typical image of a mask plate. This is the mask plate from nanoscience department here at IISc. So here engineer is holding a mask plate, and here you can see the chrome, and you can see those openings, right. Those are all the transparent regions, so where the light can go through. And this mask plate can be made out of either quartz or soda lime. So both are transparent in the region of interest, and the sizes can vary. So the mask plate size varies based on the tools that one uses, right, and the circuit one want to define, and the thickness of the substrate also can be different, because as you go for larger mask plate, you want a mechanical strength to that plate, right. So you naturally go for thicker film, and this is the reason why we choose a different substrate material. Soda lime is a very commonly used substrate material in academia and in industry as well, if your illumination wavelength is I line, right. So if you are operating at a longer wavelength, right, so you don't really worry about the absorption. So soda lime is transparent, right. So this is the transmission. But then if you are looking at deep UV patterning, you want to use quartz, because the absorption of soda lime gas increases. That means the transparency goes down, right. So you want the material to be transparent, right, when you are using deep UV. And in that case we use quartz glass. Okay. However, your quartz glass are slightly expensive compared to soda lime, but it's a trade-off that one need to make. If you want higher resolution, you should be ready to pay a little bit more. And this is how we fabricate the mask. And you can see here we already discussed this. This is captured in this process flow. You have this photo mask substrate already coated with your photoresist, and then you illuminate it with light, right. This light could be either LED, laser, or sometimes it could be electron beam, right. So, these are all the illumination that one can do, and we write it as a process, right. We do not print it, this is a writing process, and then we do the development. When you do the development, you remove the photoresist and you expose the chromium layer, and the exposed chromium layer is removed using chromium etch, and then this resist is also removed, and this is your final mask. And this is the mask writing process, right, or the writing tool we use, right. So, you can see here the engineer is holding a resist coated mask, right, with chrome, and then the design is fed into this the writing machine here, and once you load the wafer or the mask into the mask plate into the machine, it will start printing writing this layer onto the photo sensitive layer there. So, your this is called a maskless lithography. Sometimes you can use this particular writing process to directly define patterns, right. So, here we are using it to write mask, but if your circuit has a polymer, right, if you want to define a polymer, you can use this writer as a direct maskless lithography process. In this particular litho, you can use LED or laser, or for advanced CMOS mask, we use electron beam lithography. The reason for that is LED and laser will not give you the required dimension. So, here you can do close to 0.8 micrometer or so, let us say, but if you want to go to sub micron or sub nanometer scale, you need to use electron beam lithography. And this is the pattern on the mask. Once you write it and develop it, you can see here this is the chrome pattern, right, the edges and inside, and then you can look at the transparent as well, right. So, light will pass through this region, and then light will be arrested in this region, right. And this is another type of mask where we predominantly see chrome and then small openings, right. This is on the right side that you see. On the left side you see a lot of transparent region, and then the opaque regions are less, right. So, we classify this into two groups. One is called bright field and another one is dark field. When the amount of light passing through, right, this is open and this is your opaque, right, region. So, if the opaque region is much less than the open region, we call this as bright field, right. And the dark field meaning you have very small amount of area where light gets through. Okay. So, there is direct implication of either your mask is dark field or light field. We will look at that in the next lecture. So, pellicle, right, as I mentioned, pellicle is a protective layer, right. Let us look at the left side image where you have mask without a pellicle or protection, right. So, this is a rough imaging optics, right. So, you have the pattern in this plane, right, and then you reproduce it on the wafer, right. So, let us assume that there is a defect or some dust particle accumulated on this mask. So, what will happen? The dust particle will be imaged on the wafer as well. So, if there are some dust particles here, that will be imaged on the wafer as well. So, if you have open mask, it will anyway collect dust. I mean, though we use clean room for fabricating these devices, but over time you could have 1 or 2 particle contamination come and stick onto the onto your mask, and it is very hard to remove if it is stuck onto the mask, right. So that is the reason why for most of the industrial process we use pellicle, right. Pellicle is a transparent protective layer on top of the mask, right, and this is all transparent. But what will happen now, if a dust particle comes and sit on this pellicle, it won't be imaged, right, because it is not in the focal plane. So the focal plane is something like this, right. So you are now focusing your structure onto the wafer, but now the dust that is sitting on the surface of the pellicle will not be imaged, it will be out of focus. So this is how you keep the image of the dust particle out of focus from the wafer itself, so that you can avoid all these defects getting imaged onto the wafer. Okay. So this adds an additional complexity. As you can see, you need to protect it. So make sure it is tightly sealed as well. You don't want any particles going inside. It will be nicely sealed so that you avoid any damage or any contamination created to this mask. So whatever we discussed so far is a very simple mask, right, what we call binary mask, right. You have binary meaning transparent and not transparent, right. So there is complete arrest of transparency and there is no transparency. So this is what we call a binary mask, right, where we use chrome and no chrome. But there are some advanced mask technologies, something called phase shift mask. We don't use chrome to arrest the light propagation. We use phase, right, and there is alternate phase shift mask, and then there is embedded attenuated alternate phase shift mask. That is again another different type, and there is reflective mask as well. So far we discussed about transmission type mask, right. So light is transmitted, but in extreme UV, right, that is the technology that's being explored for sub 10 nanometer technology, where the mask is not anymore transparent structure anymore, right. So you are using a reflective mask. So you make a mask and you illuminate it with the light source, and then there is a reflection, right, and this reflected optical beam contains the mask details, right. It's not anymore transparent. So we will look at all these different type of masks and their interesting working principle in resolution enhancement technique, right. So with this we come to end of how we make mask, right, and what are all the important features of this mask one should take care of. It is fabricated similar to the way that we transfer image onto the wafer. The only difference is we don't do printing here, right. Printing always requires a template. So here we use a writing process. So either we use an LED, a focused LED, or a laser, a focused laser, to write patterns on this resist coated mask. And in advanced lithography masks, where your structures are very small, we use electron beam lithography. So you might wonder how you will use laser to write 100 nanometer pattern, for instance, or even smaller features, right. So the reason for that is we have this magnification. If you remember in projection lithography, your mask's dimension, the size of the patterns on the mask, are 4 or 5 times larger than the features that you want to write. So for instance, if you want to write a 100 nanometer line, your mask will be either 400 or 500. So that is within the limit of your laser beam that can be focused and written, right. So there are other resolution techniques one can use, and also for really smaller dimension we can use electron beam lithography, right. So we have a separate session on electron beam lithography. The only difference is electron has a much smaller wavelength, so that you can have a much finer features written with this electron beam. So I hope you understood the importance of this mask technology, and how we make this mask and how we protect this mask, and also how we negotiate the problem of dust collected on this mask by using this pellicle. All right. So in the following classes we will look at different type of optical litho processes pertaining to other kind of lithographies, and how we enhance the resolution as well.